recording. Okay. So if you have no questions, then I will provide you some problems. But my advice is check lecture notes before class, and maybe you will have questions. So my first question is, let's consider differential equation y prime is equal to, let's say, y cube minus 8 y squared plus 12y. Let's consider an equation like that. This is just one prime. The equation like this without time. So there are no time in this equation, just y, and no t, no x. It's called autonomous equation, but the name is not important. My main question is first find the equilibrium values of y, and point B, classify them as stable or unstable. Classify them as stable or unstable. So first question, the problem is clear. So the first question is about what we are searching for. The next question is how to search for equilibrium values, or how to check stability. But first, is everything okay with the text of the problem? Yeah.
Everything okay?
Okay, so let's solve it. What is called equilibrium value of y? So now we may solve this problem. What is equilibrium value?
It will be y squared minus 6 squared plus 12.
I don't understand. What is called equilibrium value? There are maybe you have many senses. So equilibrium has many meanings in science. So, for example, if you are studying some market clearing conditions, and you use the word equilibrium to say that supply is equal to demand. Yeah. So maybe you're right that equilibrium may refer to many concepts in science. Yeah. You may say that quantity supplied is equal to quantity demand, but in the study of dynamic systems, in the study of differential equations, and I don't know if you study some dynamic stochastic general equilibrium macroeconomic model, then equilibrium is the state which does not change over time. So there is another interpretation of the word equilibrium. Equilibrium is a state that is constant over time. It means constant over time. So there are many meanings of the word equilibrium, but in my case, I'm interested in the second one. That means constant over time, that does not change with t. And in that case, how can I solve for equilibrium values? So what should I do?
When the derivative is equal to 0,
Yeah,
so
exactly. We should
just need to equate here.
Yeah, that means if it's constant. So we have, so for example, if you are studying some, I don't know, microeconomic problem, then equilibrium may be quantity supply. So there are problems like one may introduce dynamic models in microeconomic. They would be quite difficult, but you may introduce something like quantity supply depends on T, quantity demanded depends on T, and there is equilibrium in the sense of microeconomics that for every T, quantity supply of T is equal to quantity demand of T, but they do change over time, but they do change. The equality is kept. But in my simple problem, there are no ambiguity at all. Only y prime is equal to 0 is the only possible sense of term equilibrium in my question. So that's just y prime y cubed minus 8y squared plus 12y is equal to 0. And what are the equilibria? I have an equation of the third degree. So in general, I should expect 3 roots of this equation.
Sorry, I was thinking.
Yeah. And what are the roots of this equation?
Is 2y squared by 3y squared by 2, or 16y and 12? Sorry, I don't know. It's not the answer. I'm just thinking.
Who knows the answer?
Okay, 1 is 0 at least.
Okay, 1 is 0. And what are the other two?
Is 6 and 2?
Okay, it's 6 and 2. Okay, so I have 3 equilibria in this question. So point A is done. Okay, we have found that we have solved problem A. So what does it mean? What do we mean they are equilibrium values? So for example, if you have a starting value at time t equal to 0, if you have starting value equal 2, then that means that for all t, you will have y of t will still be 2. It will be always equal to 2. If you have a starting value like 6, then for all t in the future, you will have y of t equal to 6. But if you have some value that is not equal to 0, 6, or 2, if you have some other value, so if, for example, y of at starting a moment of time is equal to, let's say, 7, then it will change. Will change over time. Okay. So we have found that there are 3 equilibria, and now let's classify them as stable or unstable. Okay.
Okay.
So how we will classify? We will draw so point B. we will draw a plot that is called phase diagram. Phase diagram. Formally, phase diagram is a general title of pictures on which some one indicator x that depends on t is plotted on the horizontal axis, and some other indicator y of t is plotted on vertical axis. In our case, we will draw phase diagram. So in general, you have two indicators. Both indicators depend on t, and you draw how they change simultaneously with t. And in our case, I will draw yt on the horizontal axis and y prime of t on the vertical axis. I know that y prime is equal to y cube minus 8, as far as I remember, y squared plus 12y. And this can easily be drawn. Who can draw the picture of this function? We need to draw this cubic function. How to draw it? How we can draw a cubic function?
There is a 3 point which y equal to 0 is from 0, 2, and 6.
Yeah, generally I agree. We can, using the roots we have found, we can factor this function into a product of 3 terms. It will be y times y minus 6 times y minus 2. I agree that if we know the roots of this polynomial, then we can freely factor our function. And if we have a factorization of our function, then we can just write 0 there, 2 there, 6 here, and we can draw this function. So when y is very big, y prime is positive. When we cross 6, the sign will change. When we cross 2, the sign will change. When we cross 0, the sign will change. So basically, we have a function like that. So qualitatively, it's not a very exact plot of the function, but it's a rough sketch. I see the points where my graph crosses the horizontal or vertical line. So it's not an exact graph, but it's a sketch. As a sketch, it's okay. And now I can easily classify my equilibrium as stable or unstable using this plot. So imagine that y0 is so just for example, let's imagine that y0 is 7. What will happen with y? What will happen with y? I can draw this point. It's located somewhere here. This is 7. And I see that at the point A, y prime is positive. Just, I don't know the exact value because I have a sketch, but my sketch is sufficient to tell that the y prime at the point A is strictly positive. I don't know the exact value. Maybe it will be 2, maybe it will be 15. I don't care. It's positive. That's all that important on that sketch. So I can, hence, I see that y will go up. If y prime is positive, then y is growing. And I conclude what will happen with y, it will grow. So starting at value 7, y will grow, but I cannot leave this line. So my two indicators, y prime and y, will remain linked by this line, and I will move in the upper right region of my phase diagram. Okay, any questions?
No questions, everything okay.
Okay, let's imagine some other point B. Imagine a point B somewhere here. That is a point B. I see that at the point B, y prime is positive or negative?
It's negative.
Yeah, it's negative. Y prime is here. Yeah, y prime and y dot is the same thing. Basically, in physics, it's a common tradition to write dot instead of derivative with respect to time. But as I have only one variable, t, then I don't care. Y prime, y dot, that's the same thing. At point B, y prime is negative, hence y will go down. If y will go down, I'm moving left on my plot. Okay. And a small question to you, if I consider point C and point D, what will happen at point C and at the point D? Will I move to the right or will I move to the left? What will happen at the point C and what will happen at the point D? A small question.
At point C, the derivative of y equals to 0. So is y equal to a one maximum point in.
No, be careful.
Okay.
If we are speaking about our plot is not a function y of x. No, our plot links y prime and y. I don't care whether it's the maximum on the graph or not.
Yeah,
To understand the dynamics of y.
So it is greater than 0, then we will move to the point 2, then it's the stable point.
Yeah, my main point, yeah, I completely agree that y prime is positive. The only thing I need, why it's positive? Because y prime is here. The same thing. Y prime, y dot, for me, is the same thing, just two different styles of notation, y prime or y dot. Okay, so it's positive. I clearly see that above 0. Hence, y will go up, but go up on my plot is to go right, because y is on the horizontal axis. So at the point C, the y will grow. That means movement to the right. So I should draw something like that. And finally, at point D, y prime will be negative. Hence, y will decrease. And I will move left. Okay, have we classified? We have not yet classified the points, but we have done 90% of the work. Now we should classify the points. If I start not at the point 6, but near the point 6, if I will start, imagine, at 6 plus some minor delta. If I will start at not at 6 exactly, but at 6 plus delta. Then I will move away from 6, okay? So the equilibrium point 6 is stable or unstable?
Then it is unstable.
No, yeah, then it is unstable, because if I add some random noise in my model, imagine that my macroeconomic model is governed by differential equation plus noise. That's a common assumption in big stochastic dynamic general equilibrium models. So, for example, central banks of all countries, they evaluate to forecast economies, they evaluate big stochastic models where there are randomness inside, and the model is not governed by only by differential equation, but by difference equation plus noise. And in that case, if a random noise, if I'm at the point 6, but a random shock arrives, a small random shock, and oop, my equation will move me away from the point 6. So the point 6, y equal to 6, y equal to 2, y equal to 0. That point is unstable. What will happen if I'm at the point 2? Imagine a random shock. A random shock arrives and moves me a little bit away from 2. A small random shock arrives and moves me away from 2. So I will go by a random shock. I will be a little bit to the left or a little bit to the right of 2. But my equation will bring me back to the point where I have started. Yeah. And so the equilibrium 2 is
Sorry, can you repeat the question?
Oh, the question, I wonder whether the equilibrium y equals 2 is stable or unstable.
Yeah, it's stable because whether we start moving from like C or B, will finally go to 2.
Yeah. Random shocks that move me away from equilibrium are not so important. They do not change the behavior of the system qualitatively, because my equation will bring me back to the equilibrium 2. And the equilibrium at 0, is it stable or unstable? Imagine a small random shock
Unstable.
that moves me away from 0, and that is unstable. Okay, so we have classified stability of equations. Oh, sorry, of equilibria, not of equation. It's not a characteristic of equation. It's a characteristic of each particular equilibrium. One equilibrium may be stable, other equilibrium may be unstable. They all correspond to the same equation. Yeah. Okay, what we can add here, we can do some more plots. We can qualitatively sketch. So maybe I will add point C, sketch possible trajectories of yt. I will not solve the equation. We can solve the equation and solve the trajectories of yt, but I will not solve the equation. I will just sketch possible trajectories of my yt. So I will have t on the horizontal axis, y of t on vertical axis, and I know that there are 3 equilibria. If I start at y equal to 6, y will remain constant. If I start at y equal to 2, y will remain constant. It's also a possible trajectory. If I start exactly at 0, my y will remain constant. But if I start at 6 plus delta, then what will happen with y if I start at 6 plus delta plus positive delta?
It will larger than 0
It will,
or higher than 0. It will increase.
yeah, it will increase. What will happen if I start a little bit below 6? What will happen with what is the qualitative behavior?
It will decrease.
It will decrease up to which number? So yes.
Up to 2.
Yeah, exactly. So it will go like that. If I start at, let's say, 2 minus 1 million, what will happen?
It will go to 2. So
So I have drawn a lot of possible trajectories of y. So I have drawn 1, 2, 3, 4, 5, 6, 7, 8 possible trajectories. Okay, so qualitatively, without solving equation, I can draw phase diagram. Sometimes I can sketch possible trajectories. Basically, that's all we can do without solving. So we have not solved equation at all. We can solve it. It's not so hard. It's an equation which can be solved by separation of variables. So if you like, we can solve it. That's not a problem. But my point of view that we can do a lot of qualitative descriptions without solution of differential equation. Okay.
Okay.
Now let's move on. I do not remember, have we discussed the number of solutions of differential equations? I don't remember. Have we discussed the number of solution, uniqueness of solution, and so on? Okay, if you do not remember, let's discuss a little bit. And if the material seems easy to you, then we will skip. The problem is the following. Next problem is, imagine that you have, once again, we discuss something that can be done without solution sometimes. So we can do a lot without solving an equation. Imagine you have an equation like that, y prime multiplied by x squared is equal to y cube. Yeah, imagine an equation like that. And the behavior depends on the starting condition, and you have some starting condition y of x0 is equal to y0. So this is initial condition. And my question is that find the number of solutions. So find the number of solutions for all x0, y0. So my question is, you have an equation, and my goal is to find the number of solutions for all x0 and y0. the problem is clear. So first question, as always, is the statement of the problem clear? So I'm not
Yeah, it's
speaking
clear.
about how to solve it. I'm speaking about the question. Is it clear?
The question is simple, easy to understand, but it's a tough question.
But there are many strategies. So let's move on to the solution. Solution. This equation is very simple. So one possible strategy is just, for this particular case, just solve it and count. Solve it and count. For this particular case, that's okay. We can explicitly solve it. And the second strategy is to use some theorems. Kirill Alexandrovich has stated some theories about the solutions of differential equations, and I will quote these theorems. I have some use existence uniqueness theorem that says if you have an equation y prime is equal to f of x and y, and if f of x and y is continuous in the region R x y such that x belongs to x0 minus, I don't know, delta, x0 plus delta, y belongs to y0 minus epsilon, y0 plus epsilon. So this function f is continuous x, y, this is x0, y0. So the function is continuous in this region. y0 minus epsilon, y0 plus epsilon. If the function is continuous in the region R, the rectangle, then in the neighborhood of x, in x0 minus delta prime up to x0 plus some delta prime, in the region x0 minus delta prime, x0 plus delta prime, there is at least one solution of differential equation. This is the existence theorem. And we also have a uniqueness theorem that says if f is continuous in R and f prime with respect to y is continuous in R, then, so if only f is continuous, then we can be sure that there is at least one solution. If it's continuous and the first derivative with respect to y is also continuous, then in the region x0 minus delta prime up to x0 plus delta prime, there is exactly one solution. Exactly one solution of differential equation. Now let's use these two theorems for our particular case. Okay, everything is clear?
Thank you, it's clear.
Okay, let's
Yeah.
use these two theorems about the number of solutions. These two theorems allow us to count the number of solutions, sometimes without explicitly solving the differential equation. Without solution, we can predict, oh, we have one solution. Oh, without solving, we can say we have 0 solutions. Oh, we have infinitely many solutions. Okay, let's do that.
So need to.
What my function?
So the strategies we're using here is based on its continuous for both x and y. And we know there at least one solution, so there must be a solution. Then we solve the problem, right?
Yeah. Okay, so in my case, y prime x is x squared is y cubed. So it follows that for x that is not equal to 0, y prime is equal to y cubed over x squared. I see that this function is, this is my f, this is f of x, y, and it's continuous for x that is not equal to 0. And my first conclusion, conclusion 1, that if x is not equal to 0, then there is at least one solution. I'm using the first part of the theorem. Then let's find f prime with respect to y. What is the value of f prime with respect to y?
Is it x squared y squared by 3?
Yeah, it's 3y squared divided over x squared. And I see that once again, this function is continuous for x that is not equal to 1. So I have conclusion 2. If x0 is not equal to 0, then there is unique solution to my equation y prime x squared equals to y cubed. Okay, so we have solved this case. Now, the most difficult part is to consider the case of 0x0 as a special case. The theorem says, oh, the function is discontinuous, so it may happen anything. Maybe there is one solution, maybe there are no solution, maybe there are infinitely many solutions. I don't know. So we need to check the special case x0 equal to 0 separately. Okay, let's check. Let's check x0 equal to 0 apart. Okay, first I look at the equation. It says y prime times x is y cube. So it follows that y prime at x0 times x0 should be equal to y cube at x0. If x0 is 0, then I may conclude that hence we have y of x0 should be also 0. Because if left-hand side is 0, then the right-hand side is also 0. So I have another conclusion. If x0 is 0 and y0 is not 0, then I have no solutions. because if I have a system like that, we have a contradiction. If y of 0 is 5, we have a contradiction. The second equation contradicts the first one. The first one says that y prime multiplied by 0 should be equal to 0, and it cannot be equal to 5, obviously. And the last case is consider x equal to 0 and y equal to 0, the most special case, the last case, x equal to 0 starting and starting y equal to 0. I don't know any other way, I don't know easy ways to avoid explicitly solving the equation. So let's solve it finally. If y prime times x squared is y cube, then dy dx is times x squared is y, and dy over y cube is just dx over x squared, and we should consider separate solution y of t equal to 0. And finally, if I have an equation like that, I add integral sign, and I have y to the power minus 2 is c to the power x minus 1. Yeah, that's okay.
Thank you. It's okay.
Oh, sorry. I need to. So if I will just take the integral, I will have what I will have here, y minus
multiplied
2
also,
by minus 2.
or
Yeah,
yeah, by 1 divided, yeah, minus 2.
here I have x minus 1 divided by minus 1. Yeah, plus constant. Okay. Any questions?
No questions.
And do not forget special solution y of t equal to 0. Yeah, because we have divided on the previous, let's call it slide, we have divided by y, so special solution y always equals to 0. And I will have this is one solution. Next solution, I multiply by 2, and I get y minus 2 equals 2x minus 1 plus, let's call it k, and y equals to square root of 2x minus 1 1, sorry, square root of 2x minus 1 plus k, or y equals to 1 over minus 1 over 2x minus 1 plus k. And do not forget that we have an initial condition that when x tends to 0, we should have y equal to 0. Remember that we have x0 equal to 0 and y0 equal to 0. And if I plot these functions, they all satisfy my initial conditions. So if I have x that tends to 0, inverse of x will tend to plus infinity, and 1 over square root of 2x minus 1 plus k will tend to plus to 0 as intended. And so if x is 0 and y0 is 0, then I have infinitely many solutions. And I have infinitely many solutions. For example, I have 1 over square root of 2x minus 1 plus 7, y equal to minus 1 over 2x minus 1 plus 15, y equal to 0, and so on. All these functions satisfy my equation, and all these functions satisfy my initial conditions. So the final answer is if x0 is not 0, then we have unique, and there is unique solution. If x0 is 0 and y0 is not 0, then there are no solutions. And finally, if x0 is 0 and y0 is 0, then there are infinitely many solutions. Okay.
Okay, thank you.
So we have discussed what we can do basically without or maybe some related topic to the solution of differential equations. So we are not always interested in just solving the differential equation. Sometimes we are interested in the number of solutions and so on.
I'm sorry, may you repeat the essential steps we need to do to solve the tasks like this? So
to find the number of solutions or to solve this differential equation? What do you mean by
solutions? Like to find the number of solutions. For example, we are given like the the equation like this. So at first we need to check what are the initial points, like x0, y0.
So if you are asked to count the number of solutions, sometimes this is possible without solving it. So in this case, you should use the theorem about uniqueness and existence of solutions. So my first advice is to use a theorem on uniqueness existence of solutions. And the theorem requires you to check whether, so you have an equation, so you should have an equation in that form. So if your equation is not in this form, y prime equal to f of x and y, then transform it into this form. And you need basically to check is to answer two questions. Is F continuous? Is F prime continuous? And maybe this theorem is sufficient. Maybe both functions are continuous. In this case, you say, oh, I have only one solution, and you do not solve the equation. But sometimes this condition fail, are not met. And if these conditions are not met, then you should try to solve actually the equation, because otherwise, because if the theorem is not applicable, then you need some other methods to find the number of solutions. And basically, we have no um, we have no general means to check. So there are, so honestly speaking, in a tough theories, there are many more theorems on existence and uniqueness of solutions. But at our level, either we use this base version of the theorem, either we try to solve it, and after solving, we just count how many solutions do we have. So if these conditions are not met, then solve the equation. Even x0 and y0, and just count how many solutions do you have. So basically, the strategy is the following. Okay, or the connection is lost. Just
Yeah, I'm listening. My question is, so our last page, the first one, if x0 not equals to 0, so there is one unique solution or there are unique solutions.
If x0 is not 0, then there is unique solution for each x. So imagine, so what do I mean? What do I mean? I mean, if you have the same equation, y prime times x squared equals to y cubed, and we have initial condition y of 2 is equal to 5. If you have an equation paired with initial condition, if you have two things, equation plus initial condition, then even without solving, no, I'm not solving, I'm saying the solution will be unique. The solution will be unique. Okay?
Okay.
So if you have an equation like that, y prime times x squared equals to y cubed, y of 5 is equal to 2. So the solution of this system of equation plus initial condition will be unique. But it will be different from the, so these solutions, y of 2 equals to 5 and y of 5 equals to 2 will give me two different solutions. Unique, I mean unique given initial conditions. Okay?
Okay.
So I'm not saying that the solution is the same for all in this initial condition. It's false. The solution is unique for that initial condition. Solution is unique for, but different for other initial conditions. And there is one exception. If you, sorry, two exceptions. If you have the same equation with y0 equal to 5, then no solution exists. Or if you have y the same equation with initial condition y at 0 is equal to 0, then we have infinite number of solutions. Okay?
Okay.
Okay, let's move on. So my advice for that type of problems is just apply theorem if possible. If not possible, try to solve. Okay, I have a simple funny question. Just for fun, but it maybe illustrates the concept of time passed, that it's a useful plot. Imagine a imagine a monk that starts. So we have a big mountain. Yeah, we have a big mountain here, and imagine a monk that starts at, so funny problem, just to illustrate the idea that time series plot may be useful. We have a monk that starts at 8 o'clock in the morning, and he starts, he goes up to the mountain, and the mountain is very big. There is some, I don't know, holy place on the top of the mountain, and he finishes his day at 8 p.m. The speed obviously is varying, so maybe sometimes he is just admiring the view, so the speed is not a constant. So just he starts at 8 o'clock in the morning and he finishes at 8 p.m. So this is day one. Day two, so the monk will sleep on the top of the mountain, and day two, he starts at 8 a.m. at the top of the mountain, and he goes down and he finishes at 8 p.m. The speed is also not a constant. The speed changes over time because sometimes the descent is very easy, sometimes it's very hard, sometimes he's just admiring the views. And my question is the following. Prove that is there a point on his path, on the path that is visited exactly at the same time. So my question, is there a point on the path that is visited exactly on the same time?
Yes, there is.
Why?
And because the progression from move on to the mountain and move out of the mountain is direct from the same line. Like the speed is increasing or speed is decreasing, and based on energy, he will put on or put out, and the change with their speed there must be one point for him is exactly at the same time.
Why? I don't understand your argument.
I'm thinking how to explain. Sorry, I don't know. And in our descriptions, that speed for these people get on the mountain and get out of the mountain is different because he's moving on and he's moving down. The speed.
Yeah, the speed is changing. Yeah, the speed is changing. I've said twice that sometimes he's admiring beautiful views, sometimes he's resting, sometimes the path is steep and it's hard to go. Sometimes the road is very easy. Yeah, the speed changes over time. Yeah, my point is that the speed of the monk is not a constant.
So my answer is not clear. Maybe yes, maybe no. Because in our last task, and if there is a solution when xo is not equal to 0, so there is a unique solution.
My main point is just let's draw the picture. So we have done, so my main point is that you are not always interested in the solution. Sometimes it's interesting to draw a qualitative behavior. So in my case, I will draw the path. I will draw what happens with my monk. So imagine that this is day one. Day one. It's time. That is 8 a.m. That is 20 or 8 p.m. This is the top of the mountain. This is the bottom. And I know that in the morning he started. At the evening he finished on the top of the mountain, and the trajectory is something like there. So this is a period of rest. He was just sleeping 1 hour uh, during his way on the top. So sometimes he's just resting. Sometimes the road is very easy and he's going fast. So the speed is not a constant, but it's a plot how his height, the height of the monk, the height where he's located, his coordinate depends on t. And if I draw the same plot, for day two, he starts at 8 a.m. He finishes his road at 8 p.m. But the plot is different. Yeah, he starts at the top of the mountain, and maybe he just goes down, 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 down. Then he is resting with a small dinner, and then he continues his way down. Maybe the plot, the speed are completely different. But my point that he starts at the top of the mountain and he finishes at the bottom of the mountain. But if I superimpose these two plots, then I will have something like that. If I just draw the same thing, these two curves on the same plot. And hence I see that at that moment of time, I don't know, maybe it was 13, maybe it was 1 p.m., I don't know. But obviously these two plots will intersect because one is going from lower left corner to the upper right corner, and the second one is going from the upper left corner to the bottom right corner. These two lines are continuous. The monk is not teleporting, he's just moving continuously. Yeah, is continuous. The graph is continuous function. We have no teleports for our monk, and so there obviously there exists a point, even he's accelerating or decelerating randomly. So in any case, there will be a point. In any case, there will be a point on the mountain that is visited exactly at the same time. Okay?
Yeah, okay. It's
I
amazing.
think that's a great problem about time series plotting, and it's very easy, very funny. So basically, that's all for today. We have covered existence of solutions, uniqueness of solutions. We have found found equilibria. We have discussed how to check the stability or instability. That's all for today. Have a nice evening.
20
If you
minutes.
have any questions, then just don't be shy. Post them in the text chat or just ask them before the class starts. So I'm always ready to answer a question.
Yeah, I have one small question for this
Yeah.
graph. So the idea about this is because it's from the same processing reverse, so it means the two graphs must be at least have one point intersect with each other.
Yeah, there should be at least one point where they intersect. There may be even many points if he discovers that he has forgotten something. So if he discovers that he has forgotten his hat on the top, so the plot will be like this. If he discovers, so he goes back to the top and goes down. In this case, you will have 2 or 3 intersections. There may be many more intersections than one if he forgets something and goes up and down during his day, but at least one.
Wow, thank you.
Okay, bye-bye.
Okay. Yeah, super fun. That's awesome. This is really, it's like a short movie somehow.
Okay, bye-bye.
Bye-bye.